All right. Hello, everyone. Thank you for introduction. So I'm a software engineer working at Facebook/Meta kernel team. I've been on the team for the last 8 years. And so I'm going to assume that most of the people here, they know what BPF is. So I'm just going to do a very, very quick overview just to set the expectations. It's also interesting fact that we're a week away from BPF birthday. Exactly 9 years ago, when Dave Miller applied the big patch set that introduced the concept of the instruction set, the system call, that was exactly in September 9 years ago. A lot of things changed since then. But the interesting fact that for BPF, tracing was kind of the beginning. BPF started as a tracing tool, as observability tool. And since then, lots of folks wrote different performance analysis tools. And in this picture, you can see that Brendan Gregg was obviously prolific, taking his dtrace tools and converting them to BCC. He wrote a book. The whole book is about tracing. And now it's even translated to Chinese. I only found out a couple of weeks ago, which is also pretty amazing. The book is 400 pages. So really cool stuff. So but beyond performance, beyond observability, people doing fun stuff with BPF as well. So if this was this is actually the video, but it doesn't play on the PDF. You can play Tetris, and that whole Tetris is rewritten completely as a bpftrace script. So some people say, I'm hearing it all the time, that BPF is not Turing complete because it cannot loop, cannot blah, 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 but it has enough of looping ability, let's say, that games like Tetris are possible to implement, which I think is a fun. So, quick overview of BPF. So, this is a different way of saying what it is. So, BPF is a sequence of commands that can be understood. And this is one of my favorite movies where Amy Adams is from the movie Arrival, is trying to explain aliens how to exit VI. Not sure whether she was successful, I don't remember, but that's what BPF is trying to do. It's sort of this universal assembly language, and its main properties, it's strictly typed. Unlike the normal assembler, where you can access anything, you access just bytes in memory. BPF assembler, it actually specifies every memory allocation what it's typed, that it's a structure, whether it's an integer, whether it's a string, and so on and so forth. Use cases. Also, it's, I think, important to recognize that once assembler has this property of being understandable, being verifiable, now it's what people are using BPF for today is user space telling kernel what to do effectively, and kernel understands this intent. But there are now innovative use cases for BPF where it's sort of done from the other side. When the hardware boots up, and as part of the hardware bring up, hardware tells kernel what to do. So it's user space to the kernel, and now hardware to the kernel. And because it's possible to do, because of this understandability of the instruction set. Similar, some companies using BPF to talk user space to user space. When one computer is talking to another in a cloud, it's delivering this message, do this for me. And because of this property of understandability, it's becoming possible. So that's how BPF differentiates itself versus pretty much every other instruction set. To some degree, one can argue that, well, x86 is also understandable. CPU can execute one instruction, or ARM. In BPF, it's not only instruction. It's instruction plus its type plus the whole sequence of the instructions that understandable. So the intent of the program, the verifier understands the intent of the program. And in this case, it can optimize it further. And that's the difference of BPF from a WebAssembly or Rust. The typical WebAssembly is a sandbox concept. when you have a sandbox, the sandbox restricts the stuff that is executing. It doesn't know what is going to be executed, like a Chrome browser, like a JavaScript or V8. Like they all restrict the stuff. They put the boundaries hard as they can get, and then let it run in there. Whereas BPF is a different like philosophy. The verifier first understands everything, like everything about the program, and then it executes. That's why there is no like runtime overhead for anything that BPF does. And that's the main difference of like WebAssembly. Even Rust is also in this category. Like Rust is like puts the boundary of the compiler for the language, whereas assembler here is like the kernel knows what it's going to do with it. Another interesting fact is that people say, oh, what's the BPF versus eBPF difference? Well, back in 2013, when this stuff landed in the kernel, it was actually iBPF. And well, thankfully, Apple is not going to sue us. So it's meant to be for internal. And for like several years afterwards, we had leftovers of this iBPF name in the kernel. And eventually, everything was like cleaned up and renamed to eBPF. Also, some people think that BPF is a static instruction set. Turned out it was extended many times. It's like now like 5 times. In LVM, there was different variations of what we call different CPUs, V1, V2, V3. And now the V4 landed a couple months ago. And now like both GCC and LVM support this latest instruction set and extension of the extended BPF. And this is what we're going to standardize and in the process of standardizing the whole instruction set at IETF. So if you're interested in helping us, please participate. In BPF, we also have what we call a mission statement of BPF. It's actually only 2 statements. One is innovate, and the second, enable others to innovate. I believe that in every project, it's super critical to clearly articulate the goals, the mission statement of the project. This is what brings developers together. This is how they know why they are like hacking on a particular feature, why they're debugging the bug. So this is why I work in particular still work after 10 years on the same project. My friends that I rarely meet like a year, like every few years, they're like, oh, what are you doing? I'm like, well, I'm still doing the same stuff. I'm still doing the same stuff because it enables me to innovate. It satisfies my own thirst for innovation. And when I see patches on the mailing list, somebody proposing either like fixing a bug or adding a new feature, like you can imagine when it's a new feature, when it's something like innovative, that's like my heart is racing and I really enjoy the work that I do. And this is what happened in the community. So I have the stats since 2019. So this is the last 4 years. This is kernel only. And the blue line is a number of unique monthly developers on the BPF mailing list. And green line below is number of developers at Meta. At Meta, the team stayed roughly the same. We had like few people join, few people left, but overall roughly the same. But you can see the growth in the community. From 40 unique developers a month to now we're like clearly above 100. So imagine the number of emails that we receive every day. I have a different graph, not going to show it. It's actually 70 emails a day that the team of BPF reviewers and maintainers have to process. So it's a huge volume of traffic. I'm going to skip this. Okay, back to tracing. As I said in the beginning, the first hooks where BPF engine was used was K-probes and U-probes and trace points roughly at the same time, and that's like started the revolution of observability. Brandon Gregg wrote this book, like people worked on, started like several months later, bpftrace project was created, BCC project created, launched, and so on. Here I want to stress what they call line of contact between kernel and BPF. And I hear often enough that from people who don't completely understand BPF, they think BPF can do so much, and in their minds it's just like everything possible. And the other people that say that like, oh, it cannot do like anything, like people who are actually like trying. So here, for the tracing use cases, BPF can read everything. It cannot write. Though people still like mistake that, oh, like if I'm attaching a tracing program somewhere in the kernel, like what is going to happen? The kernel may panic, or like BPF can write arbitrary memory and so on and so forth. So like despite years of the development, there are still people in the community, whether they really don't know or somehow some people still think that tracing BPF programs can modify state. And here is not quite the case. There are other types of programs that can actually modify state and different types of it. So there is a whole category that we call BPF networking. That's what people do to develop their own like firewalls, load balancers. And there, BPF is allowed to modify, but also this line of contact between the kernels and BPF is also limited. It's limited that it can only modify and drop the packets. It cannot like write arbitrary kernel memory. But there are other, I will talk about them later, program types where the BPF can actually change other parts of the kernel, like TCP BPF congestion control algorithms. They can influence, they can change internal TCP state to state machine, but they cannot change anything else. So BPF is this full of surprises, let's put it this way. So back to tracing. So for the tracing, I mentioned that people think that BPF, some say that BPF can do everything, some say that BPF cannot do much at all. For example, what BPF can do now is, these use cases, I really love them. In particular, the first one, explain why kernel returns e-inval. So this is done with a tool that's called redsnoop. And in the kernel, there is no like clean error propagation mechanism. For example, in the netlink, recently was added the extended ACK, that there are strings sort of that kernel return with the error code. But in a lot of cases, the system call, when something fails in the kernel, it just says error. And this error typically will be like e-inval. And at this point, if you're not a kernel developer, for the user developer, you're doing like a library, you have no idea what happened in the kernel. So with BPF, this tool like redsnoop, it allows you to construct which part of the kernel actually returned this e-inval. It will show you the path, how this error happened, which part of the kernel code first found the error condition somewhere, and how this error like propagated through the whole call chain inside the kernel, and why eventually like user space received this e-inval as a message. So this helps. So this tool like was immensely helpful to anyone doing this tight user to kernel development, and in particular even to understand why BPF system call returns the e-inval. Like you're trying to create a map and it says the e-inval. Is it the key size was too big? Is it the value size was too big? Maybe max entries was not specified. So there can be bazillion of different conditions. So another interesting one is with user probes and BPF, we can measure things that typically looks like. For example, recently I saw people measuring how much time GCC spends in processing like pound includes in a wellness compiling C++ application versus the rest. This is without instrumenting GCC. You put a uprobe, you put a small BPF program, and you just do make. And because uprobes attach not to a process, but they attach to inode, to a file, all of the GCCs that start in a system by the make, they will get out magically instrumented by the kernel with the uprobes, and BPF will measure the time delta that takes for the compiler to process includes versus the rest. And that's how like people can decide that, oh, maybe I'm like should optimize stuff. Another fun use case, if you have the Android phone, like if you're looking at your phone now, the time you spend on Facebook or you spend on YouTube, this is actually done, it's calculated by the BPF program that runs at every Android phone. And Google then like charges you depending on traffic. In the networking, I said we have many different hooks in the kernel. This is the eye chart diagram. Don't need to. You can use your phone if you want, if you're a networking heavy person. So this is all the hooks we added over the last 10 years, and it's interesting how BPF started as a socket filtering mechanism, but then it went through the networking stack everywhere, including XDP. Which is our answer to user space bypass mechanisms. Skip it. How much time do I have? Yeah, so security is another interesting topic. But I want to talk more about what is coming. As the next sort of area where BPF is going to be used. One is human interface devices. This feature's already landed. What BPF can do is something like this. It's a small program that can change how your not necessarily keyboard, but how this device looks. So this is an example where so there is a device that can be used either as a mouse or as a, I forgot, the trackball or something. So, and because of the HEAT protocol, it can only be one way. So this program can dynamically override whether it is going to be a mouse or whether it's going to be a trackball or modify other parts of the driver. So with this HEAT BPF facility, people already starting writing this mini drivers as BPF programs, which I think is pretty cool. Another use case that is coming is we call SCADAXT, is a programmable scheduler. It's effectively another scheduling class. It works. The program needs to implement a set of callbacks when task is being queued or dequeued, when it changes state from runnable, task balance and so on and so forth. And once it is done with BPF, we can do scheduling that would be, let's say, impractical for a general purpose scheduler to do. The example of it would be scheduling for the cloud. When you have multiple VMs running on the system, you don't want the standard CFS scheduler or even EVDF to keep messing with the VMs, because there is a scheduler within a VM and there is a host level, hypervisor level scheduler, so they will be in conflict. So the special scheduler that Google folks actually doing with this, they disable ticks, they completely disable ticks on the CPUs where VMs are running, and schedule everything from the one global CPU. They call it global scheduling. So it's kind of Linux kernel schedule, but very specific to cloud task. And there are many different examples why these programmable schedulers are necessary. Changing gears completely. I'm sure you've seen what ChatGPT can do. You can ask him all sorts of stuff, including weather in Bilbao today. Not sure it will be correct answer, but I asked him, that's exactly what I wrote, write a BPF program that parses IPv4. And I didn't change a single character in this output. So AI apparently now can not only speak and understand BPF, it can write BPF based on the human input. And this is actually pretty much correct. The program itself is correct. It's doing sensible stuff. And AI even inserted the comments there. So they are not mine comments. Do something with IP address, that's what AI is saying. I'll skip this. So before last year, what we had in a kernel was this whole set of hooks where BPF can attach and do something with it. And that was all done in a, I would say, more or less hard-coded way. we realized that this like hard-coded setup, hard-coded contract, let's say, pre-specified contract between kernel and BPF runtime, it makes things a bit more rigid than kernel developers would like to see. So there was a concern that this like BPF everywhere is making the kernel harder to innovate and maintain on its own. So that's why almost like 2 years ago, we switched to this, what we call new tracing, where everything is sort of like a tracing program, but everything is unstable as well. So there is no specified like hooks anymore. Like BPF can attach to any function, and it knows its arguments because like we annotate the whole kernel with type information. Program has its types, and the kernel has its types. So we don't like attach to a fixed hook like we had in the past, like skbuff or XDP metadata. We can attach to the kernel, to like everywhere in the kernel. So the whole kernel becomes accessible to the program. So it's sort of we are tracing the kernel, but at the same time we whitelist certain operations where programs can influence the kernel in a certain way. So this is how, for example, scdxt is done. There is no like stable API. It's like kernel to kernel contract, and everything can change at any time. So the main goal here is to help maintainers of the various kernel subsystems like scheduler, fuse, to be comfortable that BPF is not gonna like dictate any kind of rules, that it's an aid to the programming, and it's not gonna like, there is no ABI or stability guarantees. Quickly about restricted C. Like 10 years ago when we all started, like BPF was a one program. So it was, that's why it was called like BPF program. Then we introduced sub-programs, and what happened like earlier, like 10 years ago, all programs had to be always in line. Like when you write in C, you would have to specify this always in line to force compiler to collapse all of this function into one giant function. And that obviously like didn't scale that well. So about like 4 years ago, we changed the compilers, changed the kernel, changed the libbpf, and now like all of this is gone. So they can be proper, there is a proper support for global or static functions. Loops was an interesting story. At the beginning, we didn't have any loops whatsoever, and users to even write a simple construct like for I to whatever 10, they would need to add pragma unroll. That's obviously people hated it, so we added bounded loops where the verifier can determine this that the loop eventually bounds, and sort of trying to solve the halting problem somewhat successfully. Now we added iterators where it's sort of like C++ iterators where you can tell the kernel to iterate over certain object. In this case, this bpf4 is a macro that iterator over integers. We have a similar iterator that iterate over task, iterate over C group context, or iterate over map element. So all of this, the concept of C++ iterators, we took into C language effectively. Another part is that actually I'm getting to the main point of this presentation is I'm arguing that the extended C that we've created for BPF is a better way to program, will be a better way to program everything in the kernel in the future. So BPF is not something that we're doing just for tracing. BPF started as a tracing, but it went through networking, security, now scheduler, the patches for BPF and selection and detection logic are being proposed. There is a Fuse BPF project also going on. So this extended C, I believe, is a better way because it's a safer C. For example, in a normal C, you can just typecast any pointer to any other pointer and just dereference, and most likely the kernel will crash. In a BPF C, this is not allowed. Like the verifier will catch this kind of mistakes. Then same for things like a use of the free. In a normal C code, you will just do it, and well, you will be double decrementing the reference count potentially of this socket, and things will not go well. Where in the BPFC, like verifier catches this type of wrong reference counts mistakes. Another interesting bit is type tagging. We've extended C with type tags. And if you program the kernel, I'm sure familiar with like underscore CU, underscore user tags. And for the kernel, the user one is only sparse annotation. Sparse might catch you and like give you a warning. That's basically it. Underscore CU is slightly better. It's not only sparse, but RCU machinery. If you compile the kernel with full RCU debug, and do RCU dereference, use RCU dereference macro outside of RCU critical section, there will be a kernel splat. But if later you dereference, then you do RCU unlock, and then start and access this RCU pointer, nothing in the kernel can help. Like this type of mistakes are just like impossible for the kernel to catch. So it has to be the whole like compiler and the verification system together to catch this type of mistakes, and that's exactly what we do in BPF. In BPF now we have this explicit RCU read lock unlock primitives that behave just like normal RCU, and on RCU unlock we invalidate all the pointers that are valid only in RCU critical section. So if program is trying to dereference it, the verifier will reject it. So that's a safety aspect of it. Then we did a bunch of other cool things, like we saw how the concept of unique pointer and shared pointer in C++ I think are pretty useful. So we carried over similar stuff into this extended C. We have a concept of kind of like unique pointer where we compare change. But yeah, I'm going a bit too far. Since I'm out of time, I will conclude with this summary. So when people consider what are they going to use to extend the kernel, whether to write a BPF program or write a kernel module, well, obviously kernel module is, you can write everything in there because it's the free C. You can access all the export symbol, all the memory, but there will be like security considerations, like compiling on the host is not fun. Whereas in BPF, you have safety. And unlike kernel modules, BPF is debuggable because all the types are present in the kernel. We even store the source information as part of BPF object. So when you're dumping the kernel, it's not like, yeah, it's a kernel module foo that's doing something, but the program itself has the source code. And we're thinking of how to extend this, give even more visibility beyond what exists today. And I will conclude with this statement. We believe that this flavor of C language that is a better choice for the kernel programming. And the way we're working on the core, we're trying to make it that any subsystem, if they wish to choose BPF to write the next kernel feature, they can just do it. Just use the core, don't even talk to BPF maintainers or don't even message mailing list. So we're trying to make it as this is a generic tool for kernel programmability.
All right, thank you for your talk, Alexei. Is there any question from the audience? Edwin?
I have a question about memory usage and resource bounds. So you said you cannot crash the kernel because you can only read. Can I set some memory bounds on how much memory you can allocate in the BPF program?
Yeah. So for the memory, there are two ways actually to enforce this. One is for the traditional way of allocating memory is all the BPF maps, and all the maps, they have this max entries parameter. Beyond that, they won't allocate it. And now we have all the memory allocations are done in memcg. So once you start, you say like memcg limits, and it will do it even at runtime. Because this new one, this BPF obj_new operator is actually allocated dynamically on the fly from the program. So it's like malloc, but not kind of like kmalloc, but it's done in a safe way. And it restricts itself to memcg limits. Does that answer your question?
Yeah, thank you.
Other question? Mathieu?
This might be a topic more for the unconference after, but the overall topic I'm wondering about is interaction of reading all kernel and potentially user space memory through uprobe with things like GDPR.
With things like what?
GDPR, so a privacy law. What can be done on production systems, what is allowed to be done on production systems by system administrator in terms of user privacy. And I think this is going to become a very important topic in the observability area more and more as the laws are put in place and enforced and everything. Because if you can allow any system administrator to read any user data, then there might be issues, or you might simply be unable to use that tool on a production system and be limited to use that in a lab. So I wonder, what are your thoughts about kind of allowing eBPF to read a subset of pre-identified information that would not contain kind of private data?
Yeah, that's an excellent question, and that's been on top of the mind of many people for now years. We had this topic discussed at last LSFM BPF, and I think the one before as well, because namespace in BPF programs into at least just into some container, some memory restriction is, yeah, that's what one of the main problems that people want to solve. And we discussed several different solutions. None of them are potentially good enough. So it's still work in progress.
Yeah. So we can hash that out in unconference session, though.
Yes, but absolutely necessary, yeah.
Good.
Other question? All right. Well, thank you for your talk.
Thank you for inviting.